What if everything you've ever seen, touched, or even imagined, every mountain, ocean, or sprawling city, was just a single grain of sand on an endless cosmic beach? The universe doesn't just defy our understanding of size, it shatters it, stretching beyond the limits of human comprehension. Out there, in the vast darkness between the stars, exist structures so colossal that they make entire galaxies look like fleeting specks of dust. And yet here we are, standing on a tiny blue dot, trying to grasp the sheer scale of it all. It's humbling, exhilarating, and utterly mind-bending. Think about the largest thing you've ever witnessed, maybe a towering skyscraper, a sweeping canyon, or the curve of the Earth from an airplane window. Now imagine something 1,000,000 times bigger, then 1,000,000,000, then multiply that by a number so large it doesn't even have a name. That's the realm we're stepping into today as we explore the biggest things in the universe. From superclusters, colossal gatherings of thousands of galaxies, to cosmic filaments, the invisible threads weaving the fabric of the cosmos, the universe is built on a scale that feels almost mythical. And yet, these aren't just abstract ideas, they're real, measurable, and waiting to be discovered. But here's the twist. How do you even begin to measure something so vast that light itself takes millions of years to cross it? How do scientists pinpoint the edges of these celestial giants when they stretch across billions of light years? The answers lie at the intersection of cutting-edge technology, ancient starlight, and human curiosity, a quest to map the unmappable. So, if you've ever stared up at the night sky and wondered just how small we really are, you're about to embark on a journey that will redefine your sense of scale. Buckle up, because the universe is about to blow your mind. When we talk about the biggest things in the universe, the word itself becomes a puzzle. Is it about sheer physical size, like a star so wide it could swallow our solar system? Or does biggest mean mass, an object so dense its gravity bends space itself? Take UY Scuti, a red hypergiant star so vast that if you placed it where our sun sits, its surface would reach beyond Jupiter. But then there's TON 618, a supermassive black hole with the weight of 66 billion suns crammed into a space smaller than our solar system. One is a ballooning titan of gas, the other an invisible knot of pure gravity. So which is truly bigger? It's like comparing a mountain to a neutron star, both awe-inspiring but in utterly different ways. This is where cosmic structures rewrite the rules entirely. Imagine a single galaxy as a bustling metropolis, with stars as its streets and planets as houses. Now picture thousands of these galactic cities bound together by gravity, forming a sprawling supercluster, a continent of light and matter stretching hundreds of millions of light years across. These aren't just random gatherings, they're the universe's grand architecture, filaments of galaxies woven into a web so vast it makes individual stars seem like specks of glitter. And just like a spider's silk, these threads are nearly invisible until you step back to see the whole tapestry. But here's what's even wilder. These structures don't have edges in the way we think of them. There's no signpost marking where one supercluster ends and the void begins. Instead, scientists map them by tracing the gravitational dance of galaxies, like following breadcrumbs through an infinite forest. So when we ask, what lies beyond? The answer might not be a wall or a boundary, but a horizon of understanding waiting to be pushed further. Even when we stretch our imaginations to their limits, the scale of the observable universe remains almost incomprehensible. Picture this, a sphere around us measuring 93 billion light-years across. filled with galaxies, stars, and mysteries. That's the observable universe, the portion we can see from Earth, not because it's the entirety of existence, but because light from anything farther hasn't had enough time to reach us since the Big Bang. It's like standing in a vast, dark forest with a lantern. You can only see as far as the light has traveled, even if the trees stretch on forever. This cosmic horizon exists because light, while astonishingly fast, still takes time to cross the universe. The oldest light we detect, the afterglow of the Big Bang itself, has been journeying for nearly 13.8 billion years. But here's where it gets mind-bending. The universe has been expanding all that time, stretching space itself like a rubber sheet. That means the galaxies emitting that ancient light are now much farther away than they were when the light began its journey. The result, an observable universe far larger than its age might suggest. And yet, this raises a tantalizing question: what lies beyond our cosmic horizon? If the universe is infinite, then the observable portion is just a speck within an endless expanse. But even if it's finite, we may never know its true shape or boundaries. What we can see, though, is a web of galaxies and superclusters woven together by gravity into the largest structures imaginable. These filaments of matter stretch across billions of light years, forming a cosmic skeleton that gives the universe its structure. But within this observable realm, what stands out? Even against this staggering backdrop, certain objects and structures defy expectations. From supermassive black holes anchoring galaxies to vast voids where matter seems to vanish, the universe is a place of extremes. And as we peer deeper, we're constantly reminded, size isn't just about measurement, it's about perspective. The same universe that feels overwhelmingly large to us might just be a tiny corner of something even grander. Galaxies are the universe's cities of light, each one a glittering island of stars, gas, and dust, some small and compact, others so enormous they defy belief. Take the majestic spiral galaxies like our own Milky Way, with their elegant arms swirling around a bright core. These cosmic pinwheels are vast, stretching up to 200,000 light-years across. But then there are the elliptical galaxies, the quiet giants of the cosmos. Unlike their spiral cousins, these are smooth, featureless spheres of ancient stars, often growing to staggering sizes. And none outshines, or rather, outscales IC 101, the largest known galaxy in the observable universe. This behemoth spans a mind-numbing 6 million light-years from end to end. If placed in our neighborhood, it would swallow the Milky Way, Andromeda, and the space between them with room to spare. How does a galaxy grow to such impossible dimensions? The answer lies in cosmic collisions. Over billions of years, galaxies don't just drift alone, they crash, merge, and cannibalize one another. Picture two massive galaxies, each with billions of stars, slowly drawn together by gravity. As they spiral closer, their shapes warp, stars flung into new orbits, and eventually they become one. This violent ballet doesn't just create chaos, it forges titans. IC 101 likely grew by devouring smaller galaxies, feasting on their stars and gas until it became the colossus we see today. But there's an invisible hand guiding this growth: dark matter. This mysterious substance, which outweighs visible matter 5 to 1, forms vast halos around galaxies, acting like gravitational scaffolding. Without it, galaxies would fly apart, their stars scattering into the void. Dark matter's pull keeps galaxies intact, allowing them to grow larger and more massive over time. It's the unseen architect behind the universe's largest structures. So what happens when galaxies don't just merge in pairs but gather by the thousands? Imagine a single galaxy as a skyscraper, impressive on its own. Now picture an entire skyline, a metropolis of galaxies bound together by gravity's unbreakable threads. That's where the true scale of the universe reveals itself, not in individual giants, but in the unimaginable assemblies they form. The Virgo cluster is like a bustling galactic metropolis, a gathering of thousands of galaxies, each with billions of stars, all bound together in a cosmic dance by the unyielding grip of gravity. Located about 54 million light-years away, it's the heart of our local supercluster, a sprawling neighborhood where galaxies huddle close, their gravity weaving an invisible web that keeps them from drifting apart. But what's truly staggering isn't just the number of galaxies, it's what fills the space between them. This isn't empty darkness, it's a seething ocean of superheated gas known as intracluster medium, reaching temperatures of tens of millions of degrees. If you could see it with the naked eye, it would glow like a faint, ghostly fog, wrapping around galaxies like steam rising from a city's streets. And then there's the real heavyweight dark matter. This mysterious, invisible substance makes up the lion's share of the cluster's mass, acting like cosmic glue. Without it, the galaxies would fling themselves apart, their gravity too weak to hold the cluster together. But with dark matter's pull, the Virgo cluster becomes a gravitational titan, weighing in at a mind-bending quadrillion times the mass of our Sun. To put that into perspective, if our solar system were a single grain of sand, the Virgo cluster would be Mount Everest. Yet, as colossal as this sounds, clusters like Virgo are just the building blocks of something even grander. They're not the end of the cosmic hierarchy, but stepping stones to structures so vast they redefine our understanding of scale. Imagine a single galaxy as a house, a cluster as a city. Then what comes next is a continent, a supercluster, where these galactic metropolises gather into something almost unimaginable. Superclusters are where the universe truly flexes its architectural might, not just as gatherings of galaxies, but as clusters of clusters, each one a sprawling empire of cosmic cities. Picture the Virgo cluster again, that dense galactic neighborhood we just explored. Now imagine hundreds of these clusters, bound together by gravity into a single, incomprehensible structure. That's a supercluster, the universe's equivalent of a continent, where galactic metropolises are connected by vast highways of dark matter and gas. And we live inside one of these behemoths, Laniakea, a Hawaiian name meaning immeasurable heaven, stretching 520 million light-years across. To grasp its scale, think of Laniakea as a cosmic watershed. Just as rivers flow into valleys, entire galaxies are drifting toward its gravitational heart, the Great Attractor. This mysterious region, hidden behind the dust of our own Milky Way, exerts a pull so strong it bends the motion of thousands of galaxies, including ours. We're all part of this slow-motion river, flowing toward a point we can't even see clearly. Scientists still debate what exactly lies there, a dense knot of dark matter. A supercluster even more massive than we've imagined, but its influence is undeniable. What makes superclusters so mesmerizing isn't just their size, but their shape. They're not blobs or spheres, they're intricate webs with galaxies strung along filaments like pearls on a necklace. Between these threads lie enormous voids, deserts of near-nothingness spanning hundreds of millions of light-years. Together, this cosmic skeleton, filaments and voids, forms the largest observable structure in the universe. But here's the haunting question. Is this the end of the line? Are superclusters like Laniakea the upper limit of how matter organizes itself, or are they just pieces of something even grander? Some theories suggest that superclusters might be linked into inconceivably larger formations, patterns we can't yet detect because they're beyond our cosmic horizon. Others argue that gravity's pull weakens over such vast distances that these structures never fully collapse into unified entities. Either way, one thing's certain: the universe's blueprint is far more complex and far more beautiful than we ever dreamed. Even superclusters, as unimaginably vast as they are, can feel small when we encounter the true titans of cosmic structure, walls of galaxies so enormous they defy the very laws we thought governed the universe. At the top of this list stands the Sloan Great Wall, a filamentary behemoth stretching 1.4 billion light-years from end to end. Picture a river of galaxies so long that, if you traveled at the speed of light, it would take you over 1 billion years just to cross it. This isn't just a cluster or a supercluster, it's a continent of galaxies, a thread in the universe's grand tapestry woven so densely that it challenges one of cosmology's core principles: homogeneity, the idea that matter should be evenly distributed on the largest scales. Yet the Sloan Great Wall isn't alone. Lurking even deeper in the cosmic shadows is the Hercules Corona Borealis Great Wall, a structure so colossal that some estimates place it at 10 billion light-years across, nearly a seventh of the observable universe. But here's the catch: its existence is hotly debated. Some scientists argue it might not be a single, coherent structure, but a chance alignment of smaller filaments seen from our vantage point. Others contend it's real, and if so, it would force us to rewrite our understanding of how matter clumps together in space. What makes these walls so revolutionary isn't just their size, but what they imply. If the universe is truly homogeneous, structures this massive shouldn't exist. They're like finding a mountain range taller than Earth itself, an anomaly that shakes the foundations of what we thought possible. And if walls like these aren't flukes but threads in an even larger pattern, what does that say about the universe's true shape? Are we seeing fragments of a design so vast we can't yet comprehend its full scale? The answer might lie in the voids between them, spaces so empty they stretch for hundreds of millions of light-years, framing these walls like negative space in a cosmic sculpture. This is where the line between observation and theory blurs. Do these structures mark the upper limit of how matter organizes itself, or are they just the first hints of something far more intricate? As our telescopes peer deeper and our simulations grow more sophisticated, one thing becomes clear: the universe doesn't just contain wonders, it is the wonder, and we've only just begun to trace its outlines. Cosmic filaments are the universe's hidden scaffolding, threads of galaxies and dark matter, so vast they stitch the cosmos together into an intricate, shimmering web. Imagine the largest structure you've ever seen: a mountain range, a continent, even a supercluster, and then picture something that makes them look like fleeting brushstrokes on an infinite canvas. These filaments stretch for hundreds of millions of light-years, connecting clusters and superclusters like bridges across a dark ocean. They're not just random strands, they're the backbone of everything, the cosmic skeleton that gives the universe its shape. To grasp their scale, think of a river delta seen from space, countless branching veins of water carving through the land. Now replace those rivers with galaxies, each one a glowing point of light, and the land with voids of near nothingness. That's the cosmic web, a delicate balance of dense filaments and empty voids, with galaxies clustered along the threads like beads on a string. Even more striking, the resemblance to a human brain's neural network. It's as if the universe repeats its patterns, from the microscopic to the unimaginably large. One of the most jaw-dropping discoveries in recent years is the South Pole Wall, a filament so colossal it rivals the Sloan Great Wall in size. Hidden behind the glare of our own Milky Way, this curtain of galaxies spans at least 1.4 billion light-years, a reminder of how much we're still uncovering. Scientists found it not by seeing it directly. Our view is blocked by dust and stars, but by mapping the subtle tug of its gravity on surrounding galaxies. It's like hearing the echo of a giant's footsteps in the dark. But here's the real magic. These filaments don't just exist, they shape the universe. Gravity pulls galaxies along these threads like commuters on a cosmic highway, funneling them toward dense clusters where they'll collide, merge, and ignite new generations of stars. Without this web, galaxies would drift aimlessly, isolated in the void. It's the reason we can map the universe's large-scale structure at all, because matter isn't scattered randomly, but woven into this grand design. So how did these filaments form? The story begins with the faintest ripples in the early universe, tiny fluctuations in density left over from the Big Bang. Over billions of years, gravity amplified those ripples, drawing matter into the densest regions while emptying the spaces between. Dark matter, the invisible glue holding it all together, formed the first threads, with galaxies following like fireflies drawn to a wire. The result is a universe that's not just expanding but evolving, its structure growing more intricate with time. And yet, for all we've learned, the cosmic web still holds mysteries. Are filaments uniform, or do they vary in density and size? Could there be even larger structures lurking beyond our observational limits? Every answer peels back another layer, revealing a universe far more connected and far more beautiful than we ever imagined. The cosmic web isn't just a structure, it's the universe's blueprint, a master plan written in galaxies and emptiness. Picture the night sky not as scattered stars, but as an intricate spider's web glistening with dew, each droplet a galaxy clinging to invisible threads. This web spans billions of light years, built from three key ingredients: filaments, the dense rivers of matter where galaxies cluster; voids, the echoing deserts almost devoid of stars; and nodes, the bustling intersections where superclusters collide. Together, they form a labyrinth so vast that even light takes epochs to traverse its strands. Scientists didn't uncover this web by peering through telescopes alone, they built it. Simulations like Illustris TNG, run on some of the world's most powerful supercomputers, rewind time to reveal how gravity sculpted these filaments from the primordial soup of the early universe. Starting with tiny ripples in the fabric of space after the Big Bang, the simulations show dark matter, the universe's hidden architect, clumping first, drawing gas and galaxies into its gravitational embrace. Over billions of years, these clumps stretched into filaments, threading through the cosmos like veins through marble. The voids between them, they're not accidents, but the inevitable aftermath, spaces where matter lost the tug of war to denser regions. This web isn't passive, it's a dynamic engine driving galaxy evolution. Galaxies born along filaments are the universe's overachievers, fed by a constant flow of gas funneled through these cosmic highways. Those stranded in voids, they're like isolated villages starved of resources, their growth stunted. Even our Milky Way owes its existence to this web. It's perched on the fringe of the Laniakea supercluster, where filaments deliver fresh gas to fuel new stars. Without this intricate network, galaxies might never have ignited, and the night sky would be a featureless void. But here's the haunting thought lurking in every astronomer's mind. Is the web itself part of something bigger? Could these filaments be stitches in a quilt we can't yet see? Some theories suggest the cosmic web might connect to other, even larger patterns, structures so vast they'd make the Sloan Great Wall look like a crack in the sidewalk. Others wonder if the web's apparent uniformity is just an illusion, a trick of our limited perspective. One thing's certain: the deeper we look, the more the universe reveals itself not as chaos, but as a tapestry, woven with threads we're only beginning to trace. Quasars are the universe's raging infernos, hyperactive galactic cores, so bright they outshine entire galaxies, fueled by supermassive black holes feasting on gas and stars. But when these cosmic lighthouses gather into clusters, they form structures so vast they stretch the limits of what we thought possible. Take the huge LQG, a group of 73 quasars spanning a staggering 4 billion light-years, a structure so enormous it would take light, the fastest thing in existence, 4 billion years just to cross it. That's longer than Earth has existed as a planet. What makes this discovery so controversial isn't just its size, but its age. The huge LQG existed when the universe was barely a third of its current age, a time when such colossal groupings shouldn't have had enough time to form under our current cosmological models. According to the principle of homogeneity, matter should be evenly distributed on the largest scales, yet here's a quasar group so massive it seems to flout that rule. Some scientists argue it's a statistical fluke, a chance alignment of separate quasars strung together by our perspective. Others see it as evidence that the universe's large-scale structure might be more complex, more lumpy than we ever imagined. Imagine the cosmic web as a spider's silk, delicate and evenly spaced. Now picture a single thread thick as a rope, bulging with knots. That's the huge LQG, a potential cosmic anomaly that forces us to reconsider how matter clumped together in the early universe. If structures this immense existed so soon after the Big Bang, what does that say about the forces shaping the cosmos? Could gravity have worked faster or more fiercely than our models predict? Or is there something fundamental we're missing about how dark matter sculpted the universe's infancy? This isn't just about rewriting textbooks, it's about peering into a deeper mystery. If the huge LQG is real and not an illusion of perspective, it hints at a cosmos where the largest structures formed at speeds we can't yet explain. And if that's true, what other giants might be lurking in the ancient universe, waiting to upend our understanding of scale and time? The answers could lie in even older light, in quasars flickering from the dawn of creation, holding secrets we've only begun to unravel. Deep in the cosmic dawn, just 2.3 billion years after the Big Bang, astronomers uncovered something impossible: Hyperion, a proto-supercluster so massive it defied the universe's early rhythm. This infant giant, a tangled web of galaxies stretching across 200 million light-years, shouldn't have existed. At that age, the cosmos was still a chaotic nursery, matter barely beginning to clump into galaxies, let alone structures 1,000 times larger. Hyperion's discovery wasn't just a record breaker, it was a cosmic curveball, forcing scientists to rethink how the universe's largest assemblies grew up so fast. What makes Hyperion so extraordinary isn't just its size, but its structure. Unlike modern superclusters, which are dense, polished metropolises of galaxies, Hyperion is a sprawling, messy construction site, a celestial megalopolis caught mid-assembly. Its galaxies are younger, bluer, and more active, bursting with newborn stars, while dark matter weaves through them like invisible scaffolding. This isn't a finished product, it's a snapshot of the universe's adolescence, a time when gravity was still stitching together the fabric of reality. The implications ripple across cosmology. If structures like Hyperion formed this early, gravity must have worked far more efficiently than our models predicted. Maybe dark matter, the universe's hidden architect, clumped faster in the denser early cosmos. Or perhaps the seeds of these giants were planted in the first moments after the Big Bang, when quantum fluctuations etched tiny wrinkles into space itself. Hyperion suggests the universe didn't grow up slowly. It underwent a growth spurt, with superclusters emerging like saplings in a time-lapse forest. But here's the real puzzle. What does Hyperion's existence say about the universe's infancy? If such colossal structures could arise so quickly, were the initial conditions of the cosmos more uneven, more dynamic than we thought? The answer might lie in the cosmic microwave background, the afterglow of the Big Bang, where faint temperature variations hint at density differences that could birth future Hyperions. Or perhaps we're seeing the fingerprints of dark energy, subtly shaping gravity's grip over eons. One thing's certain, Hyperion isn't alone. As telescopes peer deeper into the past, more proto-superclusters are emerging, each one a time capsule from an era when the universe was still learning how to build its largest masterpieces. And with every discovery, we're reminded the cosmos doesn't play by our rules, it writes its own. Dark matter is the universe's silent architect, an invisible force shaping everything from the tiniest galaxies to the largest cosmic walls. Think of it like an ocean current, unseen but powerful, guiding ships across the water. Only here, the ships are galaxies, and the current is a gravitational pull so pervasive it dictates the flow of the entire cosmos. Without dark matter, the universe as we know it wouldn't just look different, it might not even hold together. Here's why: visible matter, the stars, gas, and dust we can see, accounts for less than 5% of the universe's total mass. Dark matter, on the other hand, makes up roughly 27%. That means for every galaxy glittering in the night sky, there's 5 times more mass lurking in the shadows, its gravity stitching the fabric of space into the structures we observe. When galaxies cluster into superclusters or stretch into filaments, they're not doing it alone. They're riding the gravitational waves of something far more massive, something we can't see but know is there by the way it bends light and tugs on stars. Picture a spiderweb glistening with morning dew. The droplets, the visible matter, cling to the silk, but it's the web itself, nearly invisible, that gives the structure its shape. Dark matter works the same way. In simulations of the early universe, scientists found that without dark matter's gravitational scaffolding, galaxies would never have clumped together so efficiently. The first threads of the cosmic web wouldn't have formed, and the voids between them would be even emptier. It's dark matter that drew matter into dense knots, creating the seeds for everything from galaxy clusters to the Sloan Great Wall. But how does something we can't see wield such control? The answer lies in its nature. Unlike ordinary matter, dark matter doesn't interact with light or electromagnetic forces. It doesn't collide, heat up, or emit radiation. It simply is, its gravity the only hint of its presence. This means dark matter can pass through itself and other matter like a ghost, forming vast, smooth halos around galaxies. These halos act like gravitational anchors, keeping galaxies from spinning apart and providing the foundation for larger structures to grow. The irony is profound. The biggest things in the universe depend on something we've never directly observed. Every filament, every supercluster, even the great attractor's mysterious pull, all of them trace back to dark matter's hidden blueprint. So when we ask, would these cosmic giants exist without it? The answer is almost certainly no. The universe without dark matter would be a scattered, formless void. It's matter too diffused to build the towering architectures we marvel at today. Yet for all its dominance, dark matter isn't the end of the story. It's one piece of a larger puzzle, intertwined with dark energy and the visible universe in a dance we're only beginning to understand. And as we peel back the layers, we're left with a humbling thought. The cosmos is far more than what meets the eye. Its true scale, its true structure, is written in the invisible as much as the visible, a reminder that sometimes the most powerful forces are the ones we can't see at all. Measuring the universe isn't like using a ruler on a table, it's more like trying to trace the edges of a cloud while standing inside it. When we talk about cosmic structures, filaments, superclusters, even galaxy walls, we're faced with a fundamental problem. They don't have sharp boundaries. Gravity's pull fades gradually, and matter distributes unevenly, leaving scientists to grapple with where one structure ends and the void begins. take the Laniakea supercluster, our galactic home. Its borders aren't marked by a fence or a sign. They're defined by the subtle slowdown of galaxies drifting toward the great attractor, but even that motion isn't uniform. Some galaxies hover at the edges, barely committed to the flow, while others plunge inward like rivers merging into a waterfall. This ambiguity isn't just a matter of perspective, it's baked into the physics of observation. When astronomers map these structures, they rely on redshift, the stretching of light as galaxies move away from us, but redshift isn't a perfect tool. The farther away a galaxy is, the more its light gets distorted by the expansion of space itself, like a siren's pitch dropping as an ambulance speeds off. Add to that the peculiar motions of galaxies' local movements caused by nearby gravitational tugs, and suddenly, a galaxy's apparent position might not match its true place in the cosmic web. It's like trying to chart a city's streets using only the echoes of car horns, with no guarantee which sounds come from which direction. Then there's projection bias, the illusion that distant objects line up neatly when they're actually separated by vast depths. Imagine holding two fingers up at arm's length. From your viewpoint, they might appear to touch, but in reality, one could be miles behind the other. The same happens with galaxies. What looks like a dense wall of light might be a chance alignment of unrelated clusters strung across billions of light years. The Hercules Corona Borealis Great Wall, for instance, is so enormous that some researchers argue it's not a single structure at all, but a trick of perspective, galaxies layered like transparent sheets in a notebook. So if measurement is flawed, how do we trust our cosmic map? The answer lies in cross-examination. Astronomers don't rely on redshift alone. They combine it with gravitational lensing, the way massive objects bend light like a magnifying glass, and simulations that replay the universe's evolution. By stacking multiple lines of evidence, they can triangulate the true shape of these giants, separating signal from noise. It's a bit like reconstructing a dinosaur skeleton from scattered bones. No single fragment tells the whole story, but together they reveal a creature far grander than the sum of its parts. Yet even with these tools, uncertainty lingers. The universe doesn't hand us tidy edges or clear labels. Every boundary we draw is a best guess, a line in the sand that shifts as our instruments improve. And perhaps that's the most humbling truth of all. The cosmos refuses to be boxed into human definitions. Its structures bleed into one another, vast and indistinct, reminding us that the map is never the territory, only our ever-evolving attempt to grasp the ungraspable. Even as we marvel at the cosmic web and its colossal filaments, there's a haunting question lurking at the edges of our understanding. What lies beyond the limits of observation? Our universe's observable portion, a sphere 93 billion light-years wide, might feel infinite, but it's just a speck within a potentially boundless expanse. Some theories suggest that the structures we've mapped, superclusters, walls, even the Sloan Great Wall, could be mere fractal threads in a tapestry far grander, repeating in patterns we can't yet see. Imagine zooming out from a single snowflake to find it's just one crystal in an endless blizzard. Could the universe's large-scale architecture follow a similar design, with domains of galaxies spiraling into even larger metastructures? One provocative idea comes from physicist Raphael Bauso, who theorizes that our universe might be one pocket among countless others in a sprawling multiverse, each with its own unique laws of physics. In this scenario, the cosmic web we've traced could be just a local phenomenon, like a single ripple in an ocean of universes. Bauso's framework suggests that what we call the universe might really be a tiny bubble in an incomprehensibly vaster reality, where space-time itself splinters into infinite variations. If true, the biggest structures we've identified would be dwarfed by the true scale of existence, their grandeur reduced to a footnote in a cosmic encyclopedia we've only just opened. Then there's the fractal universe hypothesis, which proposes that matter organizes itself in self-repeating patterns at every scale. Just as a coastline looks jagged whether viewed from space or a beach, perhaps galaxies cluster into filaments, which then form larger filaments ad infinitum. If this holds, the Sloan Great Wall might not be the pinnacle of cosmic structure. It could be a single stitch in a quilt stretching far beyond our horizon. The catch: we're trapped inside our observational bubble, like ants mapping a single grain of sand while the desert stretches unseen in all directions. This raises a humbling possibility. Our entire cosmic census, every galaxy, every supercluster, might exist within a gravitational watershed, a universal domain shaped by forces we can't measure. Beyond our bubble, space could be warped by unimaginable masses, bending the paths of galaxies into patterns we'd never recognize. Or worse, what if we're sitting in a cosmic void, a relatively sparse region that skews our perception of the universe's true density? The light reaching us might be an outlier, a distorted postcard from a reality far stranger than we've dared to guess. So are we confined by the limits of our instruments, or is there a fundamental boundary to what we can ever know? The answer might lie in the echoes of the Big Bang itself. If future telescopes detect anomalies in the cosmic microwave background, subtle fingerprints of collisions with other bubble universes, we could find evidence that our cosmos is just one thread in a multiversal tapestry. Until then, we're left with a tantalizing thought. The universe's true scale might not just exceed our measurements, it might defy them entirely, leaving us to wonder what giants loom in the unseeable dark. The Hubble volume is our cosmic backyard, the only slice of the universe where light has had enough time to reach us since the Big Bang. Picture standing in the middle of a vast, foggy field at night with a lantern. The circle of light around you represents the observable universe, everything you can see before the fog swallows the rest. That's the Hubble volume, a sphere roughly 93 billion light-years wide, containing every galaxy, star, and cosmic structure we'll ever know. Beyond it, the light from those regions hasn't had time to reach us yet, and because space itself is expanding faster than light can travel, it never will. Those realms are forever hidden, like islands drifting away over an unreachable horizon. But here's what keeps cosmologists awake at night. Just because we can't see beyond the Hubble volume doesn't mean nothing's there. In fact, the laws of physics suggest the unobservable universe is likely teeming with more galaxies, more superclusters, perhaps even structures that dwarf our Sloan Great Wall. Some theories propose these island universes could be infinite, stretching endlessly into the dark, each with its own Hubble volume, its own cosmic web, its own version of us staring back at their own limits. It's like living in a single room of an endless mansion, knowing other rooms exist but never being able to open their doors. This raises a dizzying possibility. What if the patterns we see, the filaments, the voids, the great walls, are just fragments of something far larger? Imagine tracing the veins on a leaf, only to realize they're part of a forest. Could the cosmic web itself be a thread in a tapestry so vast it defies imagination? The math hints at yes. If inflation, the universe's explosive initial growth, stretched space unevenly, it might have seeded regions where matter clumped into hyperstructures beyond our observational reach. These wouldn't just be bigger versions of superclusters. They could be entirely new classes of cosmic architecture, built on scales where gravity and dark energy dance to rules we've yet to discover. Yet for all we theorize, the Hubble volume remains our ultimate frontier. It's not just a boundary of light, but of knowledge. Every telescope, every probe, every equation we write is confined to this bubble. Even the James Webb Space Telescope, peering back at the universe's first galaxies, is still just sketching the edges of our lantern's glow. That's the paradox of cosmology. The more we learn, the more we confront how much lies forever in shadow. So could bigger things lurk in the unobservable? The answer is almost certainly yes, but bigger might not even be the right word. Out there, in the darkness beyond our light, the universe could be assembling structures so alien, so incomprehensibly vast, that they redefine the very meaning of scale. And that's the most thrilling part. The cosmos isn't just bigger than we imagine. It's bigger than we can imagine. Cosmic inflation wasn't just a moment. It was the universe's first and most dramatic growth spurt, a fraction of a second where space itself expanded faster than light, stretching a subatomic speck into a cosmos too vast to fathom. But here's the twist: inflation didn't end everywhere at once. Like a pot of boiling water bubbling at different rates, some regions of space stopped inflating early, forming stable pockets. Our observable universe might be one such bubble, floating in an eternally inflating sea. These other pockets, still stretching exponentially, could become universes of their own, each with unique physics, dimensions, even alternate versions of reality. The numbers are staggering. If inflation persists in most of space, as theories suggest, the multiverse could be generating new bubble universes at a rate that makes the number of atoms in our cosmos look infinitesimal. Some of these bubbles might be microscopic, others could dwarf our Hubble volume by unimaginable margins. And just as soap foam contains bubbles of different sizes, the multiverse might host cosmic domains where the very laws of nature, gravity, light speed, even the number of dimensions, are reshuffled. Our universe, with its delicate balance of constants allowing stars and life, could be a rare fluke in a froth of mostly inhospitable realms. This isn't just speculation, it's rooted in the math of quantum fluctuations during inflation. Tiny ripples in the early universe's energy field, stretched to cosmic scales, became the seeds for galaxies and voids. But in eternally inflating space, those same fluctuations could spawn entire universes, each with its own ripple pattern. Some might be desolate, their inflation ending too soon for stars to form. Others could be so dense they collapse instantly into black holes. And a few, like ours, might strike a Goldilocks balance, just right for complexity to emerge. So is our universe exceptional, or merely one note in an infinite symphony? The answer might lie in the cosmic microwave background, where faint anomalies could hint at collisions with other bubbles long ago. Or perhaps the key is dark energy, the mysterious force accelerating our universe's expansion. If it's not perfectly uniform, it could be a relic of our bubble's unique inflation history, a fingerprint of the multiverse. The most humbling thought: if eternal inflation is real, the structures we call colossal, superclusters, great walls, even the cosmic web, are just microscopic wrinkles in our local bubble. Beyond our horizon, the true scale of existence might be so vast that words like biggest lose all meaning. We're left with a cosmic irony. The more we learn about inflation's legacy, the more we realize how small our corner of reality truly is. What if our universe isn't just big but one of countless others, each with its own version of reality? This is the heart of multiverse theory, where the concept of biggest explodes beyond a single cosmos. At level 1, the simplest multiverse, our observable universe is just one patch in an infinite, eternal expanse. Picture a boundless quilt where every possible arrangement of matter repeats endlessly somewhere out there. Another Earth exists, another you, even a version where dinosaurs never went extinct. This isn't science fiction. It's a direct consequence of cosmic inflation stretching space beyond our observational limits. If the universe is infinite, then every possible configuration of particles must recur, making a biggest meaningless in a sea of identical cosmic islands. Then there's level 2, bubble universes. Imagine a pot of water boiling endlessly, with each steam bubble a self-contained cosmos. In this scenario, inflation never stopped everywhere. Instead, pockets of space cooled into stable universes like ours, while the gaps between them keep expanding exponentially. Each bubble could have different physical laws. Gravity might be stronger, light faster, or the very fabric of space might have extra dimensions. Some might be lifeless voids, others could harbor alien forms of existence. The chilling implication: our universe's finely tuned constants, the precise strength of gravity. The mass of electrons might just be random luck, one combination in an infinite lottery. String theory takes this even further, proposing higher dimensions where universes float like sheets in a cosmic stack. In these hidden dimensions, reality could fold in ways we can't perceive, with gravity leaking between layers. Picture ants crawling on a newspaper. They're unaware of the words beneath them, just as we might be blind to parallel universes inches away in a dimension we can't access. If multiverses exist, how does ours compare? Suddenly, the Sloan Great Wall and Laniakea Supercluster seem quaint local landmarks in a single neighborhood of a reality that might be unimaginably vaster. Our cosmic web, our laws of physics, even the concept of big could be provincial, a fleeting frame in an endless reel of universes. The true scale of existence might not be measured in light years, but in the fractal branching of possibilities themselves. Infinity isn't just a number, it's a concept that unravels our understanding of reality itself. If the universe is truly infinite, then every idea of biggest collapses into absurdity. How can something be the largest when there's no end to compare it to? Take Hilbert's Grand Hotel, a thought experiment dreamed up by mathematician David Hilbert. Imagine a hotel with infinite rooms, all occupied. Astonishingly, there's always space for one more guest. Just ask everyone to shift one room over, and suddenly room 1 is vacant. Now picture this: an infinite bus arrives carrying an infinite number of new guests. No problem. Move each current guest to the room number double their current one, and voila, infinite odd-numbered rooms open up. This isn't just math magic, it's a glimpse into how infinity warps logic, where a part can equal the whole, and nothing can ever truly be full. Now scale that up to the cosmos. If space stretches forever, then somewhere out there, every possible configuration of matter repeats not just once, but endlessly. There's another Milky Way, another Earth, even another you reading these very words in a distant corner of existence. In an infinite universe, the Sloan Great Wall isn't unique. It's one of countless identical structures, each as unremarkable as a single grain of sand on an endless beach. The cosmic web, just a thread in an immeasurable tapestry where patterns recur without limit. This leaves us with a haunting question: can infinity even be comprehended? Our brains evolved to navigate a world of boundaries, edges, horizons, beginnings, and endings. Infinity has none of these. It's like trying to picture a color beyond the visible spectrum or a sound outside the range of hearing. We can describe it mathematically, but intuitively it slips through our fingers. Even the language we use betrays us. Words like size and distance lose their meaning when there's no frame of reference. Yet here's the twist: infinity might not be the only option. Some cosmologists argue the universe could be finite but unbounded, like the surface of a balloon. Just as a traveler on a globe can walk forever without hitting an edge, light in a closed universe might loop back on itself over billions of years. In that scenario, biggest, regains its meaning. Structures could be measured against the cosmos's total volume, like fish in a vast but finite pond. The debate rages because the answer shapes everything. An infinite universe suggests a cold, impersonal reality where all possibilities play out ad infinitum. A finite one hints at something more curated, perhaps even designed. But until we find proof, a repeating pattern in the cosmic microwave background, a telltale curvature in space-time, we're left straddling two worldviews, each as awe-inspiring as the other. One thing's certain, whether finite or infinite, the universe's true scale humbles us, revealing how small our corner of existence might really be. Consider this: every human who has ever lived, every empire that has risen and fallen, every mountain carved by time, all of it exists on a planet smaller than a pixel in a Hubble telescope image of the cosmos. Earth, our vibrant blue cradle, is nothing more than a speck of dust adrift in a universe where structures span billions of light years. Carl Sagan captured this haunting truth in Pale Blue Dot, his voice echoing across decades. Look again at that dot. That's here, that's home, that's us. Against the backdrop of superclusters and cosmic filaments, our entire history is a whisper lost in the void. Yet there's a paradox in this insignificance. The same universe that dwarfs us also made us possible. Every atom in our bodies was forged in the hearts of long-dead stars, scattered across space by supernova, and woven into planets by gravity's patient hand. We are the universe observing itself, fleeting but awake. Those galactic filaments stretching across the dark, they're not just distant wonders, they're part of the same story that led to you reading these words. So how does this scale reshape our place in the cosmos? It doesn't diminish us, it redefines us. In a universe where galaxies collide like ocean waves and black holes bend time itself, our fragility is also our wonder. We're temporary, yes, but we're here, conscious, tracing the light of stars that died before our sun was born. That's the gift of perspective, to stand between the infinite and the infinitesimal, knowing we're stardust with a voice. And perhaps that's the most astonishing thing of all, not how small we are, but how wildly improbable it is that we exist at all. Even with instruments as powerful as the James Webb Space Telescope, our most advanced window into the cosmos, we're still peering through a keyhole. JWST can capture light from the universe's first galaxies, study the atmospheres of distant exoplanets, and reveal stellar nurseries hidden in cosmic dust. But when it comes to mapping the universe's largest structures, we're hitting a wall. Literally, the Hubble volume, that sphere of space where light has had time to reach us, is both our playground and our prison. Beyond it, the expansion of space outpaces light itself, locking away whatever lies in the darkness. And even within our observable bubble, there are blind spots. Galactic dust clouds obscure entire swaths of sky, while the glare of nearby stars drowns out faint signals from the distant cosmos. Take dark matter, the invisible scaffolding shaping everything from galaxies to superclusters. JWST can't see it directly, only its gravitational fingerprints on visible matter. To map its distribution, we rely on indirect methods like gravitational lensing, where massive objects bend light like a funhouse mirror. But these techniques have limits. The farther we look, the fainter the distortions become, like trying to trace a whisper in a hurricane. And then there's the cosmic microwave background, the afterglow of the Big Bang. While it's a treasure trove of early universe data, its resolution is fuzzy by modern standards, like studying a mountain range through frosted glass. This is where gravitational wave astronomy could revolutionize our vision. Unlike light, gravitational waves, ripples in space-time caused by cataclysmic events like black hole collisions, travel unimpeded through dust, gas, and even entire galaxies. Future observatories like the Laser Interferometer Space Antenna LISA could detect waves from supermassive black holes merging billions of years ago, revealing structures hidden to optical telescopes. Imagine hearing the universe's skeleton vibrate as filaments of dark matter shudder under the weight of colliding superclusters. But even gravitational waves have their constraints. They're fleeting, lasting seconds at most, and their sources are rare. To map the cosmic web in detail, we'd need thousands of detectable events, a cosmic chorus we're only beginning to tune into. And then there's the biggest hurdle of all, time. Signals from the universe's infancy are faint, stretched, and scrambled by 13.8 billion years of expansion. Untangling them is like reconstructing a symphony from a single, faded note. So what giants might we be missing? Perhaps ultra-diffuse galaxies, ghostly and nearly transparent, floating undetected in voids. Or primordial black holes, relics from the Big Bang, lurking in the spaces between stars. Some theories even suggest cosmic defects, knots in space-time from the universe's violent birth, could have grown into vast, invisible walls dwarfing the Sloan Great Wall. Without new tools, these phantoms remain hypothetical, hiding in the gaps between our data. The irony is profound. The universe's grandest designs might be just beyond our grasp, not because they're rare, but because we're still learning how to look. Every technological leap from Galileo's telescope to JWST has revealed wonders we never dreamed of. The next one could rewrite the cosmic map entirely. Until then, we're left with a humbling truth. The biggest things out there might not be the ones we've found, but the ones we haven't. Standing beneath a sky strewn with galaxies, it's hard not to feel the weight of an unsettling question. In a universe where structures span billions of light years and time stretches over eons, do our lives, our struggles, our joys hold any significance at all? The sheer scale of the cosmos seems to mock human notions of importance, reducing civilizations to fleeting sparks in an endless night. Friedrich Nietzsche once grappled with this vertigo in his theory of eternal recurrence, the idea that every moment, every breath, every choice might repeat infinitely in an unchanging cosmic cycle. If true, even our grandest achievements would become mere echoes in an eternal loop, stripped of uniqueness or progress. The universe doesn't just dwarf us physically, it threatens to erase us philosophically. Yet here's the counterpoint. What if cosmic vastness doesn't negate meaning but redefines it? Consider the butterfly flapping its wings in a rainforest, unaware its tiny motion might ripple into a hurricane continents away. In a universe woven together by gravity and quantum entanglement, no action is truly isolated. The carbon in our bones, forged in ancient supernova, binds us to stars that died before Earth formed. Our very existence is a testament to the universe's ability to turn chaos into consciousness, a miracle against impossible odds. The philosopher Alan Watts offered another lens. You are the universe experiencing itself. In that view, our awe at the night sky isn't insignificance. It's the cosmos awakening to its own grandeur. This tension between insignificance and connection lies at the heart of our cosmic dilemma. Does size diminish meaning or deepen wonder? Perhaps the answer isn't binary. The universe's scale doesn't render human life trivial. It reveals how extraordinary it is that we can ponder these questions at all. A galaxy may last billions of years, but it will never write poetry, fall in love, or marvel at its own existence. We, fleeting as we are, do. That paradox, the juxtaposition of our physical smallness and our experiential vastness, might be the most profound lesson the cosmos offers. Not that we don't matter, but that mattering isn't measured in light years. It's measured in moments, in curiosity, in the stubborn refusal to look away from the dark and say, I see you. And in that act, we claim our place, not as rulers of the universe, but as its storytellers. Long before telescopes and supercomputers, humans grappled with the infinite through stories, myths where the cosmos rested on the back of a world turtle, or where the night sky was a great serpent swallowing the sun each dusk. These weren't just tales, they were attempts to name the unnameable, to cage the uncageable scale of existence in symbols the mind could hold. The Hindu Rigveda spoke of a universe cyclically born and devoured, while Norse legends described Yggdrasil, an ash tree whose branches held the 9 realms. What's striking isn't how wrong these visions were by modern standards, but how they echo the same awe that grips us today when we stare at Hubble's deep field images. The canvas changed, but the question remains, what lies beyond the edge of understanding? Fast forward to the 20th century, and science fiction picks up where mythology left off. Liu Cixin's The Three-Body Problem doesn't just imagine aliens. It paints a cosmos so vast and hostile that civilizations preemptively silence each other, fearing discovery. Here, the infinite isn't just wondrous, it's terrifying, a dark forest where every player hides. Compare that to Contact, where Ellie Arroway's journey through wormholes becomes a spiritual reckoning with the universe's grandeur. These stories aren't escapes from reality. They're mirrors reflecting our deepest anxieties and hopes about scale. When the cosmic web dwarfs us, fiction becomes a survival tool, letting us rehearse the emotional weight of infinity. This thread, from turtle shells to trilithons, reveals something profound. Humanity's relationship with vastness is a dance between terror and transcendence. The same impulse that carved celestial maps into Babylonian stones now fuels our search for exoplanets and dark matter. We've traded animistic spirits for quantum fields, but the trembling wonder remains. Maybe that's why NASA's Voyager probes carry golden records not just as scientific artifacts, but as prayers cast into the dark, a continuation of the oldest human ritual, reaching across the abyss to whisper, "Are you out there?" So how has the infinite shaped us? It forged our religions, our art, our thirst for exploration. It's the reason we built stone circles aligned to solstices, and why we now fling robots at Mars. The scale of the universe could have crushed us instead. It became our greatest muse. Every myth, every equation, every sci-fi saga is a love letter to the void, a refusal to let enormity erase meaning. And perhaps that's the most human thing of all, to stand knee-deep in the ocean of infinity and still dare to sail. The deeper we peer into the cosmic web, the more we realize how much remains shrouded in mystery, like explorers charting a continent only to find its edges dissolve into mist. Take the question of size limits. Do cosmic structures have an upper boundary, or could there be formations so vast they render our great walls insignificant? The Hercules Corona Borealis Great Wall already strains our models. What if it's just the tip of an iceberg? Some theories suggest that beyond our observational horizon, gravity might weave even grander tapestries, where superclusters become mere stitches in a fabric stretching across tens of billions of light years. Yet others argue there's a natural ceiling, a scale where dark energy's repulsive force overcomes gravity's pull, preventing matter from clumping further. Then there's the cosmic web's ultimate nature. Is it infinite, or does it curve back on itself like the surface of a balloon? If the universe is finite but unbounded, tracing the web far enough might bring us full circle, like an ant crawling around a globe. But if it's truly infinite, the structures we see could be fractal, repeating their patterns endlessly like cosmic coastlines. The Planck satellite's hunt for curvature in the cosmic microwave background has found no evidence of closure yet. But absence of proof isn't proof of absence. Our instruments might simply lack the precision to detect the universe's subtle bend. dark matter adds another layer of uncertainty. We map its influence by watching galaxies dance to its invisible tune, but what if it's not uniformly distributed? Could there be dark continents, regions where dark matter clusters into formations so dense they warp space-time into unrecognizable shapes? Simulations hint at this possibility, showing how dark matter's whims could birth structures beyond anything made of stars and gas. And what of the cosmic voids? These deserts, spanning hundreds of millions of light years, aren't just empty, they're too empty. Their sheer scale challenges our understanding of how matter spread after the Big Bang. Are they bubbles in a cosmic foam, or evidence of forces we've yet to name? Some speculate they're imprints of quantum fluctuations frozen in time, while others wonder if they're scars from collisions with other universes in the multiverse. Every answer reveals deeper enigmas. The more we learn about the universe's architecture, the more we confront how little we know. Perhaps that's the most humbling truth of all. The cosmos isn't just bigger than we imagined. It's stranger, more elusive, and more generous with its mysteries than we dared to dream. The next frontier of cosmic exploration is already unfolding before us, with missions like the European Space Agency's Euclid spacecraft poised to peel back the veil on dark matter like never before. Armed with a razor-sharp wide-field telescope, Euclid won't just map the invisible scaffolding of the universe, it'll trace its gravitational fingerprints across 10 billion light-years of space, revealing how dark matter warps the very fabric of reality. Think of it as cosmic cartography on steroids, sketching the unseen contours of the cosmic web with precision that could finally answer why galaxies cluster where they do, or whether dark matter behaves as predictably as we've assumed. And it's not alone. NASA's Nancy Grace Roman Space Telescope, set to launch later this decade, will combine Euclid's depth with Hubble's clarity, scanning vast swaths of sky to spot primordial black holes, rogue planets, and perhaps even cracks in our understanding of dark energy. But the real game changers lurk further ahead. Imagine the Vera C. Rubin Observatory's legacy survey of space and time, a decade-long movie of the southern sky that will catch supernova flickering to life, track asteroids with eerie precision, and maybe, just maybe, spot the subtle distortions betraying hidden dimensions. Or ponder the Square Kilometre Array, a radio telescope so sensitive it could eavesdrop on the magnetic whispers of the universe's first stars. These aren't just tools, they're time machines, offering snapshots of cosmic evolution from the Big Bang's afterglow to the present day. What happens when these eyes in the sky turn their gaze upward? We might finally solve the riddle of cosmic inflation's fingerprints, or stumble upon structures so vast they rewrite the rules of gravity. Some theorists whisper of dark galaxies, invisible cities of stars shrouded in dust, or ghostly halos of dark matter drifting undetected. Others dream of catching quantum entanglement at cosmic scales, where particles separated by light years somehow mirror each other's states. And let's not forget the wildcards. What if Euclid spots anomalies in dark energy's push, hinting it's not constant but evolving? Or if the Rubin Observatory finds a galaxy where none should exist, defying our models of cosmic dawn? A century from now, our map of the universe might look as quaint as a medieval globe missing entire continents. Future astronomers could laugh at our primitive debates over dark matter's nature, just as we chuckle at the once popular ether theory. They might navigate by gravitational waves, communicate through quantum networks, or even, if we dare to dream, unearth evidence of civilizations thriving in the cosmic web. One thing's certain, the universe has never been content to fit inside our models. It's always been wilder, weirder, and more wondrous than we imagined. And the greatest discoveries, they're still out there, waiting for the next generation of stargazers to lift their eyes and ask, what else? Want to navigate the cosmos from your couch? The Sloan Digital Sky Survey is like Google Maps for the universe, a free, public archive of over 300 million celestial objects waiting at your fingertips. With a few clicks, you can zoom from the craters of the Moon to the outer fringes of the observable universe, tracing the same galactic filaments that astronomers study in their hunt for dark matter. But here's where it gets even more immersive. Apps like Space Engine and Universe Sandbox transform your screen into a starship dashboard, letting you fly through 3D models of superclusters or simulate collisions between galaxies in real time. Picture toggling between infrared and X-ray views to reveal hidden structures, or watching a black hole's gravity bend starlight like a cosmic funhouse mirror. These aren't just tools, they're portals, shrinking the unimaginable scale of the cosmos into something you can hold in your hands. Yet every time we map the universe, we're reminded how much lies beyond the edges. The Sloan Survey's most stunning revelation wasn't just the Sloan Great Wall. It was the realization that our instruments capture only a fraction of the light streaming through space. Switch to a radio telescope's wavelength, and suddenly invisible gas clouds blaze into view. Adjust for redshift, and distant galaxies leap forward from the noise. Each layer of data peels back another cosmic blindfold, revealing how much our view depends on the lens we choose. Seeing is believing, but also questioning. Why does the Hercules Corona Borealis Great Wall look fragmented in some surveys but coherent in others? Could our 3D maps be missing entire dimensions of structure, like flatlanders unaware of the sky above them? That's the magic of these tools. They don't just show us the universe, they show us how much we don't see. Every zoom in exposes new mysteries, every filter toggle hints at hidden realms. So go ahead, dive into the map, spin the virtual cosmos like a globe, but as you do, remember, you're not just an explorer, you're a detective sifting through starlight for clues to the universe's best-kept secrets. One of the most persistent myths about the universe is the idea that it has a center, some fixed point from which everything expands. This misconception likely stems from watching explosions on Earth, where debris flies outward from a single origin. But the Big Bang wasn't an explosion in space. It was the rapid expansion of space itself. Peer-reviewed studies, like those analyzing the cosmic microwave background, show the universe has no privileged center. No matter where you stand, galaxies appear to retreat equally in all directions, like dots on an inflating balloon. If you could rewind time, you wouldn't find everything converging to one spot. You'd see space itself shrinking uniformly, with every point equally central. Then there's the belief that black holes are the universe's largest structures. While supermassive black holes like TON 618 are staggeringly dense, they're minuscule compared to cosmic filaments or superclusters. A black hole might weigh billions of suns, but the cosmic web's filaments contain trillions of galaxies, each with billions of stars. Research published in the Astrophysical Journal confirms that the largest black holes influence their host galaxies, but they're mere specks within the grand tapestry of galaxy clusters. They're like knots in a spider's web, important, but not the web itself. Another common mix-up, assuming the edge of the observable universe is a physical boundary. In reality, it's just the limit of how far light has traveled since the Big Bang. Beyond that horizon, space likely continues infinitely, or perhaps loops back on itself in ways we can't yet detect. Studies using baryon acoustic oscillations, frozen ripples from the early universe, suggest the cosmos is uniform on scales far larger than we can see, with no abrupt edges or walls. Truth is often stranger than fiction. The universe doesn't just defy our earth-bound intuitions, it rewrites them entirely. What seems like a center is everywhere and nowhere. What feels like an edge is just a temporary horizon, and the true giants of the cosmos aren't the dark monsters lurking in galaxies, but the invisible threads weaving them together. The deeper we look, the clearer it becomes. Reality doesn't just surpass our myths, it eclipses them. From atoms to galaxies, scale is relative, but the universe takes that idea and stretches it beyond comprehension. Picture Earth as a grain of sand. The solar system would then sprawl across a football field, with Pluto orbiting near the far end zone. Yet even that vastness shrinks to insignificance when we zoom out further. Our entire Milky Way, at this scale, it's a dinner plate holding countless grains, each one a solar system, and the cosmic filaments connecting galaxies. They'd weave through a space larger than Mount Everest, turning our dinner plate into a single speck of glitter on its slopes. This exponential leap isn't just about size, it redefines how we perceive reality. Take the Great Attractor, a gravitational anomaly pulling thousands of galaxies toward it. If our solar system were the size of a coffee cup, the Great Attractor would be a swirling storm the size of North America. Yet even this titanic force is just one knot in the cosmic web's filaments, which themselves are threads in a tapestry stretching billions of light years. The scale isn't linear, it's logarithmic, where each step multiplies the last by magnitudes we can't intuitively grasp. Consider time alongside space. Light takes 8 minutes to travel from the Sun to Earth, a sprint compared to the 100,000 years it needs to cross the Milky Way. Yet the journey across a single filament like the South Pole Wall. Billions of years, by the time its light reaches us, the structure itself may have vanished, leaving behind a ghostly echo. We're not just seeing distant objects, we're peering into a past where the universe was younger, hotter, and stranger. Here's the twist, these scales aren't static. The universe expands faster the farther out we look, stretching the fabric of space itself. A galaxy 10 billion light-years away isn't just distant, it's racing from us faster than light can bridge the gap. We'll never see it as it is today, only as it was when its light began its journey. The cosmos isn't just vast, it's a hall of mirrors where distance and time blur, and every measurement comes with an asterisk. Yet for all this grandeur, scale is a paradox. The same quantum rules governing atoms also shape galaxies. Gravity's pull, weak enough to lose to a fridge magnet on Earth, becomes the universe's architect across light years. From the infinitesimal to the infinite, the cosmos repeats its patterns, reminding us that bigness and smallness are sides of the same coin, flipped by forces we're only beginning to understand. Neil Tyson once said, "We do science not because it's easy, but because we're curious and because it's hard." That hunger to unravel the cosmos has propelled humanity from cave dwellers sketching constellations to explorers decoding the cosmic web. But in a world of pressing problems, climate change, poverty, disease, does peering at galaxies billions of light years away truly matter? Or is cosmic curiosity a luxury we can't afford? Consider the Apollo program. Sending humans to the moon seemed like pure spectacle until its tech spun off into innovations from MRI machines to water purification systems. Similarly, the algorithms developed to map dark matter now power cancer research and climate modeling. The tools we forge to grasp the universe often become lifelines here on Earth. Even the humble CCD sensor, born in telescopes to capture faint starlight, now sits in every smartphone camera. Curiosity-driven science doesn't just answer abstract questions, it builds the scaffolding for unforeseen breakthroughs. Yet there's a deeper argument beyond utility. The act of seeking whether we find answers or not expands what it means to be human. When Galileo pointed his telescope at Jupiter's moons, he didn't just discover celestial bodies, he shattered the idea that Earth was the universe's center stage. Every time we measure a supercluster or trace a filament, we're not just collecting data, we're recalibrating our place in existence. That shift in perspective ripples through culture, philosophy, even ethics. How we treat each other and our planet changes when we see ourselves as temporary tenants in an ancient, evolving cosmos. But here's the counterpoint: mystery has its own value. Some truths might lie forever beyond our reach, veiled by the limits of light speed or the crushing vastness of space. The poet John Keats called this negative capability, the ability to dwell in uncertainty without frantic resolution. Could our relentless drive to dissect the universe sometimes blind us to its beauty? The Hubble Deep Field Image isn't just a dataset, it's a portal to awe, a reminder that wonder doesn't demand explanation. Perhaps the answer isn't either /or, but both /and. We can chase the universe's secrets with one hand while leaving room for reverence with the other. After all, the same curiosity that fuels science also inspires art, music, and myth. Whether through equations or poetry, we're reaching for the same thing, not just to understand the cosmos, but to belong to it. And in that reaching, we find something equally profound, not just answers, but meaning. There's something undeniably humbling about staring up at the night sky, isn't there? That moment when the sheer scale of it all, the swirling galaxies, the unfathomable voids, the filaments stitching the cosmos together, hits you like a tidal wave. It's a feeling that transcends language, a quiet awe that connects us across cultures, generations, and even time itself. Every civilization has looked up and wondered. Every human heart has raced at the thought of infinity. And now here we are, tiny, fleeting, and yet impossibly lucky to bear witness. So tell me, what cosmic question lingers in your mind when you gaze at the stars? Is it the mystery of dark matter's invisible grip, or the haunting possibility of multiverses beyond our reach? Maybe it's simpler, like whether we're alone in this vastness, or if somewhere in another corner of the cosmic web, another version of you is pondering the same thing. Drop your thoughts in the comments below. Let's turn this into a collective reflection, a digital campfire where we marvel together at the universe's grandest riddles. Because here's the beautiful truth: the universe's grandeur isn't just a spectacle to observe, it's a journey to share. Every discovery, every unanswered question, every star chart scribbled on a napkin ties us to something bigger than ourselves. We're stardust with smartphones, creatures of curiosity racing to map the darkness before our brief flicker of time runs out. And in that race, we find something extraordinary, not just knowledge but connection. To each other, to the cosmos, and to the endless chain of wanderers who came before us, the universe doesn't just dwarf us, it unites us, and that, perhaps, is the most astonishing scale of all.